Alright, y'all, here we go. This is the Unit 5 video, practice test video. This is part 1. Um, we're first going to start off with the notes. So in case you missed this, or you want another explanation of this, I'm going to fill this out one more time. So what is a parameter? The parameter of a 1 proportion is p. This would be the true proportion. Okay. The statistic for 1 proportion would be p hat. This would be the sample proportion. Okay. The mean for a 1 proportion sampling distribution is, and we use this symbol to represent it, mu p hat equals p. So the distribution, sorry, the mean of the sampling distribution just equals whatever p is. Okay. And then the standard deviation, that is the sigma p hat, that equals the square root of p1 minus p over n. Okay? Alright, next one. 2 proportions. If it's 2 proportions, then the parameter is p1 minus p2. That's the difference of the true proportions. Yeah, the statistic would be p hat 1 minus p hat 2. And then the mean, the mu of p hat 1 minus p hat 2 is equal to p1 minus p2. And then the standard deviation, that sigma p hat 1 minus p hat 2 is equal to the square root of p1 1 minus p1 over n1 plus p2 1 minus p2 over n2. Okay? For means, next is mean. For one mean, okay, if we have one mean, the parameter is mu. That is the true mean. Okay. The statistic is x bar. That is the sample mean. The mean is of the sampling distribution is equal to the population mean, mu. Okay. And the standard deviation of the sample mean is equal to the original standard deviation divided by the square root of n. Okay. Last one for two means. Two means it's mu1 minus mu2 is the parameter. Statistic is x bar 1 minus x bar 2. The mean is, so that's mu x bar 1 minus x bar 2 equals mu1 minus mu2. And then the standard deviation of x bar 1 minus x bar 2 is equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so these are all the formulas you need to know for the test. And so a lot of the test is just choosing which one of these is going to be and then doing the problems. Okay, central limit theorem, last thing is, the central limit theorem just says that as sample size increases, the sampling distribution becomes normal. That's all it says. Generally speaking, if the sample size, n, is greater than or equal to 30, it is normal. That's the rule. Okay? So if the sample size is above 30, it is normal. I forgot to write here, becomes normal. Okay, there we go. Alright, let's do some problems. So, on with the test. But it says, if a sports writer took a sample of 30 baseball players and found the mean Annual salary for each sample, he got the following sampling distribution measured in millions of dollars. Okay, so we got a sampling distribution here. So what does each dot represent? Well, each dot is, look right here, is a sample of 30 baseball players. These are not baseball players, okay? They are means, specifically, of samples of 30 baseball players. So they are mean salaries of samples of 30 baseball players. Okay, estimate the true mean salary in millions of dollars. Well, if I'm estimating here, well, I'm looking kind of in the center of the data set. I might guess about right here, it's kind of roughly in the middle. You know, anywhere in this zone kind of looks roughly mean-like to me. So I'm going to say roughly $4.5 million. Okay. If he instead took samples of 40 players at a time, the dot plot would be, this is narrower. And I'm going to prove to you why that's the case. If we go back to our formula sheet here, if sample size increases, remember this is the standard deviation, right? And this measures the spread, right? This measures how spread out the data is. Look what's on the bottom here. This is sample size. So as this goes up, that standard deviation becomes tighter and tighter, becomes smaller. So that's why it is going to become narrower. If sample size goes up, as n goes up, we go narrower. If n were to go down, we would go wider. Okay. That'll be better. And generally, you want higher sample sizes. That's also related to the central limit theorem because we get a more normal distribution with larger sample sizes. Okay. According to the U.S. Census, 24% of people in Redwood City are under 18 years old. We randomly select 50 people in Redwood City and found that 27% are under 18. Okay, so what's the parameter? Well, the parameter again, that's the value of the population. So the parameter here is 0.24 because that's the number in all of Redwood City we're given that are 18. Our statistic is the number that we just found. So we just found that 27% are under 18. Okay, the sample size again is given to us, that's 50, so n equals 50. And are we talking about proportions or means? Well, we're talking about proportions, we're talking about percentages, right? Okay. So again, how do you know if you're talking about proportions or means? Percentages, right? Think in your head, percentage, right? If I'm talking about percentages, I'm talking about proportions. Okay. Let's keep going here. Number 3. Katie Ching, the head of Summit, believes that 45% of Summit students prefer a B schedule. She randomly samples 500 of the 4,095 students at Summit schools and asks whether they like it. From now on, assume all conditions are met. Find the mean and standard deviation of this distribution. Okay, so in order to do this, we need to figure out what we're dealing with. Well, I see here that I have 45%, right? So this indicates what, guys? That indicates a proportion. So I immediately know to look at my proportion side of things, right? We're going to be looking at it. And how many proportions do I have? Well, just the one. I'm not taking any difference of anything. It's just one proportion. Okay, so I'm going to go down proportion, and I'm going to use my formulas. So to get the mean, the mean is just equal to the p. So I can say that the mean, u, p hat, just equals 0.45 because that is what the p is. Okay, and it's helpful in this case, you know, to mention, okay, well, p is 0.545, and the other letter that we care about is the sample size. And so the sample size here is the 500 because she took samples of 500 out of that number. Okay, standard deviation. Okay, same thing. Well, we're dealing with proportions, so we're going to follow this formula right here. So it's going to be sigma p hat equals the square root of 0.45 times 1 minus 0.45 over 500. Okay, so that's, again, that's this formula right here. Ooh, yeah, right here. I went to proportions, I went down to standard deviation. That's one I got to use. So, if you just write this, I'm pretty happy with this, to be honest with you. If you write it right, I can't really follow you too much as long as you write it correctly. But it is a really important skill, guys, to be able to calculate this in your calculator. Like, this isn't going anywhere, and it's just useful, in your future classes in life to be able to use a calculator. So I want to see you guys do it. So here we go. 0.45 times parentheses 1 minus 0.45 is 0.247. We're going to divide that by 500. Okay, and then I'm going to square root that. So second x squared, and then answer, and I get 0.022. Let's do 3 decimal places. So I get 0.022. Explain what the standard deviation means here. Use a sentence frame. So this is saying that on average, the proportion deviates by 0.022 from the mean of the sampling proportion mean. Okay, the sentence doesn't have to be exactly like that, but essentially what you're saying is we are on average above and below the mean by 0.022. So you remember this from the last test probably, that you could add that value to that and subtract that value for that, and that would kind of be your range. So in that case, my range would kind of be, so we take this, we're going to add plus 0.45, 0.472 would be my high, and then 0.45 minus 0.022, 0.428 would be my low. Okay, so we're kind of, what it's saying is we're in this range. Our sampling proportions are generally in this range. Okay, so what's the probability that she gets a sample less than 42% of the students prefer AB? So the calculator input below, then use online calculator. So on the test, I'm not going to have you use the online calculator, but I will have you fill this in. If you have a graphing calculator, I can show you how to find the probability with that. The mean is 0.45. We know that. The standard deviation, we're pulling from right here, 0.022. My lower bound, it says less than 42%. So if you think about it, look at the curve here, right? In the middle is 0.45. Well, 0.42 is right here, and I want less than. This is the region I want. So my lower bound is negative 999. It's like all the way over here. My upper bound is 0.42. That's it. Okay. If you did want to find the probability in a calculator, what you would do is second distribution, normal CDF, negative 999, comma, 0.42, comma, 0.45, comma, 0.022. And we would get about 8.6%. Okay. Again, do not have to put that, only this. This is the part I care about. Okay, last page here. A machine produces candy bars with a mean weight of 1.55 ounces and a population standard deviation of 0.05. The population is not a normal distribution. To test the machine, a company checks the first 35 bars out of the 4,000 they produce each day. From now on, assume all conditions are met. Find the mean and standard deviation of this sampling distribution. Okay, so again, what am I dealing with here? Well, it says very clearly a mean. How many means do I have? I only have one. So I'm going to go to the one mean. Okay, so the mean of my sampling distribution is just equal to the mean that I had originally, which is 1.55. Again, good habit just to mark, okay, my sample mean is 1.55, and my population standard deviation is 0.05. I'm sorry, I meant to say the population mean is 1.55, the population standard deviation is 0.05. So to get the sample standard deviation, we are going to take that 0.05 and divide it by the square root of n. I also have n here is 35. Okay, that is it. That is this formula right here. Okay, the sample standard deviation sigma divided by square root of n. Okay, so that comes out to 0.05 divided by the square root of 35 is about 0.008. What does that mean here? On average, the sample means deviate by 0.008 ounces in this case from the mean. Okay, that's ounces here, 0.008 ounces. The company's sample ends up having a weight of 1.51 ounces. Calculate the z-score. Okay, the z-score, you're going to take this value, the 1.51, you're going to subtract the mean, 1.55, and you're going to divide by the standard deviation, 0.008. Okay? This is kind of what it looks like in symbols. It's that my sample mean minus that my sampling mean divided by my sampling standard deviation. That's what I'm doing. So when I do that, I get 1.51 minus 1.55 divided by 0.008. I get -5. Okay. What is the probability that they get a sample with a mean greater than 1.51 ounces? Show the calculator input. So the mean is 1.55. Standard deviation is 0.008. Lower bound would be, so I want greater than 1.51, so 1.51 is my lower bound, and upper bound is 999. Probability, if you have a graphing calculator, would be second bars, normal CDF, 1.51, comma 999, comma 1.55, comma 0.008. Close it, done. About 70%, 0.69%. Okay, and that's it. If you're done this is on, I'm not here this day, but if you're done at this point, and you feel good about this, finish the con, get the points, guys, finish the con, okay? All right, that's it.